So you have two plates, top and bottom. Okay, as you can see here, this is your plates, top and bottom. You have V1, positive V1, and you have V2, negative V2, right? Why become negative? Because of axis, right? Since x-axis positive in to the right, so meaning V1 is positive. So that's why V2 become negative. Okay. Before that, this question does not give you the what the velocity profile. Okay. So this drawing, I draw it for you. Okay. How we came up with this one? Let's take a look this previous example from the notes. Right. See this one. Okay. So you have a fixed plate at the bottom, right? And you have a moving plate at the top. Okay, when you move in to the right, so what happens is your velocity profile will look like this, which is a triangle. So you have a straight line, vertical line, and then you have a triangle, also a straight line. Okay. All right. Yeah, because of x component, so your velocity will be u velocity, and then the change of u towards y direction, right? So basically, y del u over del y not equals to 0 because of there is a change of u towards y. So the magnitude of arrow, for example, here is 0, and then become larger towards the or become longer when it move to the top. So for example, this is 0 velocity, 2, 4, 6, 8, and 12, right? So what happened is, u is actually changing in towards y. So del u over del y cannot be equals to 0. There is a change of u towards y direction. So similar to this one, but first you need to draw the velocity profile, right? By using this information or your knowledge on this, so since your plate is moving in opposite direction, you have two triangles. One to the right, another one to the left. So, and it cross an axis, which is y. Okay. So any question up until this point? Any question? I'm okay. Everybody okay?
Okay, sir. Okay.
Alright. Alright. So next is after we establish u component and the change of u towards y, next what we do is we want to apply assumptions, right? So assumption number 1 should be steady flow. Okay. Meaning it does not change with time. right? Yeah, this profile will always look the same at any given time, right? Because of V1 and V2, for this case, it's going to be the same, right? So this profile will look the same at 8 o'clock, 9, 10, 11, 12. So basically, it's going to be a steady loop. So that is assumption number one. Okay, assumption number two, there is no flow in y direction, right? Your flow is only in x direction. Therefore, v equals to 0. Okay, that is assumption number. Alright, assumption number three is fully developed laminar flow. Okay. So now I'm going to explain what is fully developed laminar flow. So I'm going to use this figure. Right. In a part, you have a part. Perhaps the part is from an elbow, right? So just exit of the turn of the elbow, you're gonna perhaps the velocity profile will look something like this. Okay, smaller and become larger, right? So the velocity perhaps 1 meter per second at the top, 2 and 1. For the next velocity profile is 2, 3 and 2. And after that, next is become 2, 4, 2, for example. So for this region, we call this as a not fully developed flow, right? Because of the profile is still changing. So that one is not fully developed. So how about fully developed? For a fully developed flow, the profile will look the same. It's no different. Okay, so I put numbers here, easier for you to understand. 2, 4, 2, and next profile the same, 2, 4, 2, and 2, 4, and 2. So this one is fully developed laminar flow. Alright. Okay, so now you know the component velocity is u, right? So how to mathematically represent fully developed flow, right? So the flow is actually in x direction, okay, component x. So now, del over del what? Is it del u over del y? Is it del u over del x? Is it del u over del z? Anyone?
Del U over del X.
Del u over del x, very good. Equals to? So you have del u over del x. So mathematically, we can put it del u over del x equals to 0. Right? Any question? For fully developed laminar flow. So in x direction, the profile will look the same. Okay. But for this region, no, right? So here, del u over del x for this region is not going to be equals to 0. del U over del X for this region is not going to be 0 because there is a change of component velocity in X direction. 1, 2, 1, and then suddenly become 2, 3, 2, and then suddenly become 2, 4. Right? So since we assume fully developed laminar flow for assumption number 3, so del U over del X equals to. So any question?
No, sir.
So far okay?
Okay.
You should be able to differentiate because we use 2, right? We have del U over del Y just now. And then after that, we have del U over del X. So please make sure you are able to differentiate why we use those two terms in our equation. Alright. So next, number 4. Okay, there's no flow in Z direction. So since there is no flow in Z direction, W equals to 0. And then del over del Z equals to 0. But for assumption number 2, del over del Y is not equals to 0. Okay, only V equals to 0. Because of, we already established that del U over del Y is not equals to. So those are the 4 assumptions that you can apply, right? For any case, in fact, right? When you apply Navier-Stokes equation, meaning number 1 is going to be steady flow, number 3 fully developed laminar flow. 1 and 3 should always be there for any problem in this chapter. Okay. The thing is, for number 3, perhaps the mathematical equation or term instead of del U over del X maybe become something else. For example, let's say if I change this one, now this is actually Y. And then this one's perhaps Z. Alright, tell me, what is going to be the component velocity now?
D over dy.
Component velocity is what? Not D
D
over D.
D over dy.
Sikit lagi. We have velocity in Y direction. Meaning, instead of U,
V. V.
dv over dy.
yeah. The component velocity should be V, right? So for fully developed laminar flow, it's going to be del V over del Y. Right? This one is equals to 0. This is for fully developed. Fully developed laminar flow. So how about the change? V changes with what?
U. W is Z. W.
Del V over del Z is not equals to 0. Okay, right? So hopefully you understand. Okay. So I change back this one, or perhaps only okay. You already understand. So take a look at the axis. Really important. What are the axes involved? Either x and y, and or perhaps z and y, for example. So it's going to be changed. Okay. But still, number 1 should be steady. Number 3 should be fully developed laminar. And number 2 and 4 based on cases. For example, just now you have y and z, right? So your component velocity you already found is actually v. So meaning number 2 should be no flow in x direction. Okay, for that case, let's now I'm going to change this axis. Right. So I put back to our problem. Alright, this is not your profile. This is the example for me to explain what is fully developed laminar flow. This is your profile for this case. Okay. So next, we're going to apply these assumptions towards two equations. Number 1 is continuity equation. Number 2 is Navier-Stokes equation. Okay. So we always start with continuity equation. Alright. So this is continuity equation. Okay, we start with del rho over del t plus del rho u over del x plus del rho v over del y plus del rho w over del z equals to 0. I mentioned in the previous class, this is the general equation for continuity equation. Okay, so number 1, I cancel out del rho over t, del rho over del t. I put it 1 because of, our assumption is steady flow. It doesn't change with time. Okay, next, we need to cancel out, or not cancel out, since rho is constant. Why rho is constant? Because your problem is incompressible. Okay, so I want to emphasize here, for chapter number 2, even there's no mention about whether the flow is compressible or incompressible in the question. You always put our problem as an incompressible flow, because if you have a flow in a pipes or any plate, the fluid flow is going to be slow. Okay? The velocity not until at a certain Mach number. Okay, so that's why we assume incompressible. So remember that, even though there no mention at all in the question, unless for chapter 5. So meaning chapter 2, chapter 1, chapter 3, chapter 4, always incompressible. Right? So since you have incompressible flow, the density is constant. That's why here, as you can see, I can cancel out density. It's not 0, it's actually constant. Meaning the density, I can move it to the right hand side, multiply with 0, becomes 0. Okay. So you left out with this del u over del x plus del v over del y plus del w over del z equals to 0. Okay, alright. Perhaps somebody already know, okay, our problem is always steady flow, which is based on assumption. And Sir Imran also told me, you are a student. And after that, you already know chapter 2 always incompressible flow. So if somebody just directly put this kind of equation, meaning you don't cancel out this one, it's also there's a mark for it. So meaning I know that you are actually understand. So value over del x and so on. Okay, open up your camera, please. The one who just joined.
It's 9 hours.
Okay. Alright. Next, I cancel out, or we can cancel out del v over del y, right? Because we know this one. In fact, don't need for this whole thing. Yeah, even though the whole term is cancelled out, the one that we cancel is v actually, because we don't have any component v. Our fluid flow only u. Okay, so v is cancelled out. Similarly, we cancel out w. Okay. The component w we cancel. So number 2 and number 4. No flow in y direction, no flow in z direction. Okay, so done with continuity equation. Any question?
No, sir.
Okay. Whatever that I want to deliver to you, then translation. Okay. Alright, next is we need to apply Navier-Stokes equation. Okay. So Navier-Stokes equation, you have three components: component x, component y, and component z. Okay. You only have a u component, so that's why y component and z component you totally cancel out, right? So what we need to do is we just solve this x component only. Okay. Right. So next is try to solve or simplify the Stokes equation. Okay, take a look at the first term. Okay, we have del u over del t. Number 1. What is number 1 just now?
Steady flow, sir.
Steady flow. What is steady flow? Del over del t, right? So that's what we cancel out. Okay. U. Can I cancel out u?
No,
No. Because of what?
because in x direction.
Yeah. Because our velocity is actually in x direction. Right? Next is del u over del x. I cancel out this one. Number 3. What is number 3?
0.
Fully developed laminar.
0.
Number 3 is fully developed laminar. For del u over del x, you can also use continuity equation, because we already established here that del u over del x equals to 0. So either one. Okay, next is v. why I cancel out V? Yeah. Number 2, right? There's no flow in Y direction. Okay, next is W. Why I cancel out W?
No flow in Z direction.
No flow in Z direction. Okay. Del U over del Y here, so I balik. Del U over del Y here, I cannot cancel. To be there. Okay. But the thing is, yeah, since I cancel out V, meaning the whole term is cancelled out. So, no, right? So the whole term is cancelled out. Since V equals to 0. We get back here. So del U over del Z, also I cancel out due to number 4. Right? Del over del Z equals to 0. Alright, done. Okay, next is pressure difference. Okay, del P over del X. Why I cancel out pressure?
Incompressible.
Density constant.
Apa? Just to under. Sorry.
Incompressible density, not pressure.
Steady flow sir.
No, steady flow only for del over del T. Right? So for this case, del over del T, that is steady flow. So why I cancel out pressure?
Tu soalan cakap no applied pressure.
Yeah, correct. Because there is no applied pressure in X direction. Your sentence is correct. Soalan cakap sebab tiada applied pressure. Okay. Now, hear me out. Please hear me carefully. Right? Okay. For this case, it's actually a closed system. What is closed system? When you have a fluid in between plates. You have top plates, top plate and bottom plate. So if you have a fluid in between plates, should have pressure difference actually. Should have pressure difference. Okay. So in actual, for this case, we cannot cancel out pressure difference. But the question itself ignore the pressure. Right? So that's how we can cancel out. Okay. If you have this kind of problem, see, del P cannot be cancelled out. Cannot be cancelled out. But since the question itself ignore the pressure difference, so we just cancel. We follow the question. The one that del P over del something equals to 0, when you have something like this, if you have a fixed plate at the bottom or any plate at the bottom, and you have a fluid at the top of it, and then does not close by any plate. I mean, it's open to atmospheric pressure. So that's why, imagine you actually living in an atmospheric pressure. Atmospheric pressure, is it the same? Anyone? Can you give me the atmospheric pressure value? Nur Izwani, what is the atmospheric pressure value? Thank you. 101,325 Pascal, right? So atmospheric pressure, you are living in an atmospheric pressure, but the one is actually perhaps for flower, and you are actually moving higher at higher elevation, the pressure will be different. But those plate occurs at a certain pressure level. So when it is open, meaning the pressure acting on the fluid is going to be the same when it is open. So that's why for this case, this symbol meaning it open to atmospheric pressure. So del P over del X equals to 0. Then we can cancel out. Okay. Right. Understand?
Understand, sir.
Okay. So I already explained um, the behavior of pressure um, for a closed system and open system. So that's it. That is for pressure. Why we can cancel, why we cannot cancel. Okay, next is gravity. Gravity 0. Why 0? Gravity. Okay, Shami, open your camera. Okay, why gravity 0?
No gravity in X direction.
Okay. Simply say your plate is actually in horizontal direction. Or the fluid move in horizontal direction. That's the simple term. Because gravity acting vertically to the bottom. Okay, towards the bottom. So the fluid is flowing, not influenced by gravity. The velocity profile looks like that because of something else, but not due to gravity. But for this case, it's due to the plate movement at the top and bottom in opposite direction. So that's why we can cancel out gravity. Okay. Next is we go to the shearing term. Second order of shearing. So you have mu del squared u over del x squared. I cancel out due to number 3. Del u over del x equals to 0. Fully double laminar flow. Del squared u over del y squared. I cannot cancel out because that is our problem. We already established that del u over del y is not equals to 0. And the last one is del squared u over del z squared. We cancel out due to number 4. There is no flow in z direction. Okay, that's it. Any question? Ada soalan?
So yang gravity tadi sana sir?
Gravity. Alright. Gravity here gravity acts in the negative y direction, meaning towards the bottom, right? Okay. But your fluid is actually flowing in horizontal direction. Okay, and the fluid flows because of the plate movement in opposite direction. Okay, the velocity profile looks like that because of those plate movement, not because of gravity. And simply say, we what simple for you to synthesize this one is, if you have a gravity gravity in y direction, but your problem is horizontal, yeah, cancel out gravity. That's it.
Okay, sir.
Is it okay?
Yes, sir. Okay.
Clear, right? Is it clear?
Yes, sir. Clear.
Anything else?
Saya nak tanya,
Yes?
nombor 2 tu V is equal to 0, kan?
Yes.
But du dy does not equal to 0.
Yeah. Okay.
Apa?
Alright. Normally, when we want to apply assumption number 2 and number 4, okay. Okay, if you want to put it something like this, right? Okay, this is different to the one that to the question that being asked by your friend. If your arrangement, I mean steady flow at number 4, say laminar flow number 1, up to you. Okay, doesn't matter. Okay. Now I'm gonna explain about number 2 and number 4. Okay. Number 2 and number 4 here is actually about flow. So we know that the flow is only in U component, right? U component. So number 2 is there is no flow in y direction. So V equals to 0. See here, y direction. So we need to establish y. Is it del over del y equals to 0 or not? Okay, take a look at no flow in z direction. Once again, we establish two terms. One is the component, and one is the direction, del over del z. Okay. So for w component, w equals to 0. Del over del z also equals to 0. Okay. Why? The answer is the same. Okay, later I'm going to explain. Here also v equals to 0. And we need to establish as well that what happened to del over del y. So here is del over del y is not equals to 0. Due to what? The answer for both del over del y and del over del z, y become like that because of this. Del u over del y, we already found it is not equals to 0. How we find this one? Yeah, based on the velocity profile. U changes with y, right? The explanation is 0, 2, 4, 6 until 12, meaning it changes in y direction. So that's why del over del y, it's not equal to 0. I cannot cancel out. Alright, is it clear?
Yes, sir.
Okay, anything else? Okay. So we almost halfway to our solution. Okay, next what we do is, after we cancel out all this term or simplify all this term, we left with this. Okay, you can see here is mu del squared u over del y squared equals to 0. y0 because everything else is cancelled out here to 0. So what you have is mu del squared u over del y squared equals to 0. Okay, what we want actually for this case, we want is actually u. We want to know what is the u equation. Okay? And it's actually based on the equation. Derive an expression for the velocity distribution, meaning u, right? Alright. So mu del squared u over del y squared equals to 0. So you have mu, we put it there, so meaning cancel out, right? Kita pindahkan ke sebelah kanan. And then next we solve for differential equation. So we need to integrate del squared u over del y squared, integrate both sides, left and right. So 0 integrate becomes c1. So del u over del y equals to c1. And then we integrate another one, right? So hopefully you understand based on that. Why I put it there? It's the integration. So when we integrate del u over del y become u. C1 become C1y plus C2. Okay. So we haven't yet finished, completed our Roche distribution equation because we want to know what is our C1, what is our C2. We need to have this unknown. Okay. How we're gonna find that? We're gonna use boundary condition. So BC1 and BC2, right? Boundary condition number 1 is this. Once again, up to you. Which one is BC1, which one is BC2? Up to you. So, but here I put this one as BC1. Is it? And this one is BC2. So, what is boundary? Yeah, we're talking about boundary itself. So, this is boundary. Boundary condition. Right? Okay. So, now take a look at X and Y. The position of X and Y is actually at the bottom. Okay, why? Later I'm going to explain the importance of axis positioning. For this case, it is actually at the bottom. So here you can put it as at y equals to 0, at the bottom, right? 0, u equals to negative v2, direction of v, right? And then at y, BC number 2, at y equals to h, u equals to v1. Okay. So what happened if your x and y is positioned at the center? If your axis is positioned at the center, what happened to the boundary condition number 1? Anyone? The height is still the same, h. So at y equals to what?
H over 2. Haha.
Yeah, correct. At y equals to negative h over 2. Because of the y is actually positioned at the center. and u still equals to negative v2. Okay. And for boundary condition number 2, for axis at the center, at y equals to positive h over 2. And u is still the same, v1. Right? So now you know the importance of axis positioning. Apatah lagi kalau this is totally bertukar. Let's say this is z, this is actually no y. Let's say this one is actually x, for example. So meaning now, here is not at y, now become at
X.
x. Yeah, now become at equals to negative h over 2. Okay. Alright. That's it. We get back to our problem. So BC number 1 is at y equals to 0, u equals to negative v2. So what happened to your problem is you're going to apply this boundary condition at equation 1. Okay. So meaning u equals to negative v2. C1y, y is actually 0 plus c2. Remember, what we want is actually, we want to know what is the value of c2 and c1. So here is c2 equals to negative v2. Yeah. Okay. So next we go for BC number 2, boundary condition number 2. At y equals to h, u equals to v1. So once again we use equation number 1. So now u become v1, c1h, but c2 we found previously is negative v2, so we just put it there. So in the end what you have is c1 equals to v1 plus v2 divided by h1 negative plus divided by h. Now we know our c2 and c1. So now last step, we need to put back those c1 and c2 into the first equation or equation number 1. So u equals to v1 plus v2 divided by hy negative v2. That's it. That's the final answer for this problem. Any question? Ada soalan? No question? All clear?
Clear, sir.
Okay. Right. Okay, so now we go to we get back to our problem. Case A and case B. Right? So yeah, you have a fixed plate at the bottom, moving plate at the top. So the flow is actually triangle, and X and Y is positioned at the center. So since the height given is 2h, so meaning you're gonna have plus h and negative h. Right? So for BC number 1, at y equals to negative h, u equals to 0. And at y equals to positive h, u equals to b. Okay. So that is for case A, fixed plate and moving plate. We call this as fluid flow. There is a special name for it. And next we go to case B. Okay, case B is you have a flow between two fixed plates, but still you have a velocity of fluid flow or fluid flow. Um, how does the fluid flow is due to pressure difference? Without any pressure difference, there's no fluid flowing at all. Right. Okay, so boundary condition, once again, at the bottom, BC1, at the top, BC2, and you can have another one here, at the center. So BC1, BC2, and BC3. Okay, so somebody give me BC1. Who want to try BC1 for this case? Anyone? Or perhaps I call names. Okay. Hana Rafifa. Can you give me your answer for BC number 1?
Y equals to positive H.
BC1 at the bottom.
Oh, sorry. Y equals to negative H. And then U tak sure sir.
U equals to what? At the bottom here. This one is fixed
U,
plate, right?
U equals to 0.
Yeah, because the plate is fixed, correct? So there is no fluid at the, just near to the plate, to the at the bottom. Right, very good. So that is BC number 1. Thank you, Hannah. All right, BC number 2. I cannot see his name. Chat. Muhammad. I can only see Muhammad. Can you see me? You are here actually. Muhammad what? Can you see my cursor? You. Muhammad Syahmi. Okay, Syahmi. BC number 2.
Y equal to H.
Sorry, can you speak up? I can't hear you.
Yes, sir.
Yeah. Now clear.
Y equals to H. Betul, sir.
Yes, correct.
U equal to 0.
Yes, very good. Right? So at y equals to h, u equals to 0. Okay, that is BC number 1. Thank you, Shami. That is BC number 1 and BC number 2. Okay. I mentioned just now we have BC3, which is positioned at the center here. So for BC number 3, well, you can put it there because of there is a distinct obvious, okay, because of really obvious that we can put a boundary condition in this position. Okay, how basically it's actually u maximum here. Okay, u maximum. So how we represent u maximum is at y equals to 0, y0, because of at the center, right? Y position at the center. The axis is position at the center. So at y equals to 0, del u over del y equals to 0. Meaning, this is also mean that u is actually u max, maximum velocity. But we don't normally use this one instead of, yeah, we know that is the phenomena. But the thing is, mathematically, we put as del u over del y equals to 0. Okay, why? Take a look here. Before it reach at the center, the u is changes. 2, 4, 6, 8. Perhaps 8 is the maximum. And after that, it goes back to 6, 4, and 2. So it cannot go further than this. So meaning just nicely at the center, there is no change for you at that position. Right? So that's why del u over del y equals to 0. Okay? And it is also mean that u is actually u maximum. So we're going to use this one as your boundary condition if needed. Okay? Because sometimes you apply BC1 and BC2, you are not able to determine C1 and C2. Okay? You need to use BC number 3, for example. Okay? Alright, that's it. So that is case A and case B. And then, yeah, you not only have that, we also have vertical direction. Okay? Either one is fixed, another one is in motion. Be careful on the axis even. And perhaps you also have fixed plate. Okay. Maybe the profile looks like this because of what? This is simply because of gravity, right? The fluid is flowing down. So once again, you can apply the same concept. This is BC number 1, this is BC number 2, and this one is BC number 3. The only difference is the direction, either horizontal, vertical, and all. Okay, done. Any question? Yes? Yes? Yeah, so that's why del u over del y equals to 0. Right? Constant, right? Meaning there is no change. Correct. What you assume is correct. It's actually constant. Meaning u maximum, yeah, u is actually maximum. Constant now. Anything else? Okay, so we still have time. Normally I give you rest, but no, right? Because we start a little bit late due to my problem just now. So we continue with another example. This is January 2018. Okay. What is the time now? 9:40. All right. So you have a liquid flows down an inclined plane surface in a steady, fully developed laminar flow of thickness h. So this question is bagus lah, baik lah. Okay. Why? Because of dia dah bagi tahu dah. Okay. Steady and fully developed. And without that also, even though tak bagi tahu, we should assume that okay, steady flow and fully developed. If not, we're not able to solve the problem. If not fully developed, because of there is a change, right? Kalau ada perubahan, macam mana kita nak solvekan? Okay. So assume that number 1 and number 3, right? Steady and fully developed. Okay. Simplify the continuity equations and Navier-Stokes equations to model this flow field. Clearly state all assumptions. All right. Okay, for this exam question, something is wrong there. This one should be x. And this one should be y. So your component velocity is still u. Okay. And also del u bersabarlah dengan saya ya. Sebab saya punya pen problem. Del over del y is not equals to 0. I try to solve the pen for the next class, if possible. Okay, there is change of u towards y. Nampak? Del u over del y is not equals to okay. Right. So next is assumption, steady flow, no flow in y direction, v equals to 0. And then you have a fully developed laminar flow. So the same. U does not change with x. So del u over del x is going to be 0. Okay, imagine this is the same. Sama je. Imagine this drawing is the same. Meaning there's no change of u towards x. Okay. Do not confuse with the angle because our axis follows the flow. I mean, the orientation of the axis is follow the inclination of the plate, right? Unless if your problem is like this, but your axis is straight. This is a totally different solution. Okay, totally different solution. Right. So since this one is inclined, the same like the plate inclination. So yeah. So almost the same with your solution. But imagine, how about if the axis is not given? So you actually an engineer, right? Later. So we try to solve the problem as simple as possible. So yeah, you can put it anywhere, whether you want to put it at the center or you want to put it at the top. Okay. But based on your experience, perhaps you can put it at the bottom, for example. And easier for you to solve if your axis is inclined together with the inclination of the plate. So you try to solve it using like just now, the answer is going to be quite difficult for you to find. So fully developed laminar flow, once again, you have del U over del X. Equals to 0. So that's what the last one, number 4. Semua sekali jawab. No flow in what?
Z direction.
Z direction.
Minta you all tulis dekat kertas you all. Saya tulis ni lambat. Jangan follow saja. So meaning W equals to 0. But not yet complete, right? We have another one. Del over del apa ni? Del over del Y. Is it equal or
Not
not?
equal to. Not.
Not equal to 0. How about this one?
Del over dz
Del Z
del z equal to 0.
equals to 0. That's it. See? The same assumptions, the same number of assumptions. 1, 2, 3, and 4 enough to solve any problem for Navier-Stokes equation. Sebenarnya ada 5, but those 5 tu dia tak sama, so no need. 1, 2, 3, 4 is enough. Okay. Yang 5 tu adalah gravity and all. Tak apalah. It depends. So just follow me. 1, 2, 3, and 4 is enough. Okay, next is what? What is the next step? Kita kena buat apa? Ada 2 equation that you need to solve.
Continuity equation.
Sila buat solve continuity equation. Okay, so if you see me here, I didn't put the row, just directly put the continuity equation, which is incompressible and steady. Yeah, you can do like this as well. Okay, so which one to cancel? Del U over del X, del V over del Y, or del W over del Z? Everybody.
Del V over dy
And
and
Del W over DZ.
you know why, right?
Yes.
Because of no component V and no component W. So similar, del over del Z. Okay, tapi yeah. So in actual, the whole thing is cancelled out. So this is number what? Number 2 and number 4. Okay, done with the continuity. Next is never stop. Okay, so I give you perhaps 3 minutes. Solve never stop equation. Okay. Um, Muhammad Najmi. Okay. How to remove pin. Okay, I'm talking about X component and Y component and Z component. Can I cancel out, Najmi?
Yes, sir.
Yeah. Can I
Yes.
cancel out? Oh, okay. Your answer is yes. Why?
Because there is no component V and W.
Yeah. Very good, Najmi. So we can cancel totally. This is not easy, eh? Because of what? Because your problem is incline. This is actually a common problem with your senior previously. When they encounter an inclined plate, they thought, yeah, should be two dimension. So later, since they have X and Y, sorry, they thought that X and Y component is there. Only Z component they cancel out. So what happened is the answer should be wrong. For a vertical or horizontal problem, clear. Okay. But sometimes you make a mistake on this. Okay. Very good, Najmi. So we only have U component, almost similar to what we done previously. Okay, so next is del U over del T. Ramai Muhammad. Najmi. Irfan. Del U over del T. Can I cancel out?
Cancel out.
Number
Because
what?
of number one,
Number
steady
one.
flow.
Yeah. Very good, Irfan. Okay. How about you? Syami dah. Hana dah. Nurul Anis. How about you?
Cancel. Cancel.
Sorry? Come again.
Cancel.
U component.
Tak. You tak cancel. U over dx cancel.
Okay, alright. So U is not cancelled out, but del U over del X cancel. Very good. Why?
Ikut summation nombor 3.
Fully developed, right?
Yes.
Very good. Thank you. Alright, next is the next term. Dania. Putri Dania.
V is cancelled out.
V cancel out. How about del U over del Y?
Del U over del Y. Tak. Kot.
Tak kan, Dania? Tengok
Tak.
ada code. Kan?
Because of assumption number 2.
Yeah. There's no flow in Y direction. Very good. So this is number 2. Okay, thank you, Dania. The next term, del U over del Z. So Z. Afzatul Najwa.
Cancel out.
Because of
Number 4. No flow in Z direction.
no flow in Z direction. Okay, next we go to the pressure difference. Del P over del X. I have lots of Muhammad. Not easy for me to determine. Okay, Muizzuddin. Muhammad Muizzuddin.
Yes, sir.
Yeah. Del P over del X. Can I cancel out or not?
Yes, sir.
Remember back Muhammad Muizzuddin when I explained about open and closed system. This is open system, meaning
Okay.
Muizzuddin.
Yes, sir.
Open system meaning
Dia punya pressure, sir.
yeah, the pressure.
Pressure dia ATM pressure.
ATM pressure. So meaning
Oh, so we cannot cancel lah.
no. ATM pressure meaning the pressure acting on this problem is always the same, right?
Oh.
Kan?
Oh, ya.
Yeah,
Luar
yeah.
dengan dalam.
Yeah. So anywhere, kat sini, here, to the right, to the left, the pressure acting is always the same, which is P ATM for this case. So meaning, since is it the same?
So we can cancel it out.
Yeah, very good, Muizzuddin.
Okay, sir.
So this one we can cancel out. Nothing's there, but yeah, this one you should know. Alright. Gravity, rho GX. Natasha Najib.
Yes, sir.
Okay, Natasha. How about gravity? Can I cancel or not?
Cancel. Yeah. Sorry. Tak boleh cancel kot.
Why? Very good.
Because questions tak cakap pun gravity dia tu.
Oh, no. The reason would be if you have a plate which is in horizontal direction, like this, right? Natasha. And then you have a fluid flow on top. Fluid is actually on top of the plate.
It's 10 hours.
So when we put it and incline, now the fluid is flowing. Those fluid flowing due to what, Natasha?
Gravity.
Yeah. So can I cancel or not?
No.
All right. So yeah, very good. So we cannot cancel. Okay, sorry. Should be there. Should be there. So rho G X. Okay. Next is del squared U over del X squared. This one is number 3 code. Okay, number 3. This one is del squared U over del Z squared. This is number 4. Okay. Right. So now your equation becomes 0 equals to rho G X plus mu del squared U over del Y squared. So slightly different with your previous problem. Alright, so that's all. So we continue on Tuesday. Any last question? Ada soalan daripada anda? Right. Fill in your attendance. Yes, Irfan. Any question?
No, sir.
Fill in your attendance now. So I'm gonna put on the GC ruang for you to submit your assignment. Okay, later after this, I'm gonna put that. So you can submit your assignment before next class. Just refer to the GC where to submit your assignment. So baru 23, I still have another 6 or 8 students.